My name is Alex Hart, and this presentation is based on a research paper about why antimatter is superior to other particle modalities in radiation therapy. But before we discuss that, it is important to get a better understanding of what antimatter is. Antimatter is almost exactly the same as matter, with just a few key properties reversed, with charge being the most obvious property. Another notable fact is that when matter and antimatter meet, they completely annihilate each other. In the first moment of the Big Bang, extreme heat enforced perfect symmetry of energy. Then, when the universe was still less than 1 nanosecond old, energy coalesced into equal amounts of matter and antimatter. The problem lies within the concept of symmetry. Remember that when matter and antimatter meet, they completely annihilate each other. So, when an equal amount of matter and antimatter came into existence, they should have destroyed each other, and we, along with the entire universe, should cease to exist. In 1964, physicists discovered that antimatter can decay more rapidly than matter. Now we experiment with B-mesons, which are especially heavy particles, by studying their rate of decay to further unveil asymmetry and to help explain why matter exists. The theory of leptogenesis, although incredibly complicated, explains this asymmetry by using a seesaw. Neutrinos morphed into antineutrinos, which pulled the lepton side of the seesaw down, and the amount of ordinary matter had no choice but to increase. Therefore, one of every billion antimatter particles changed into matter. Antimatter then destroyed 99.9% of matter. Then atoms such as hydrogen, deuterium, and helium began to form. The next 15 billion years, atoms coalesced into stars, galaxies, and us. Throughout the years, there have been a number of discoveries and experiments that can account for our knowledge of antimatter today. It began in an equation that eventually led to a discovery that will continue to shape technology for many years to come. In 1905, Albert Einstein published his theory of special relativity, explaining the relationship between space and time and energy and mass in the famous equation E equals mc squared. It was then expanded upon in 1928 by Paul Dirac, who created an equation that predicted antiparticles by combining Einstein's theory of special relativity and Schrödinger and Heisenberg's quantum theory. In 1932, Carl Anderson discovered the positron, or anti-electron, proving the existence of antimatter as predicted by Dirac. The next particle physicists would find was the antiproton, which has most practical uses, including radiation therapy. Shortly after the first time it was produced in a lab in 1932, antimatter began showing up in science fiction. It began with C.T. Stock, then quickly made its way into Isaac Asimov's book, I, Robot. Yet neither compared to the legacy and influence of Star Trek. Since 1966, the Starship Enterprise has been whizzing through the universe via antimatter as fuel. According to NASA, most self-respecting starships in science fiction stories use antimatter as fuel for a good reason. It is the most potent fuel known. Albert Einstein said, "If an idea does not sound absurd, there is no hope for it." His theory of relativity gave us a source of nuclear energy that gave us a way to power a spacecraft and travel stars. The ideas that came from science fiction gave rise to further research and experimentation with antimatter. It was through this research and experimentation that scientists realized that certain unique properties of antimatter are better suited for cancer therapy than any other particle. The antiproton beam is unique because it not only spares normal healthy tissue while leaving the body, but it also deposits a higher concentration of energy into its target in a more accurate manner. Here is a graph depicting the energy deposition between the protons, the leading particle in radiation therapy, and the antiprotons. As you can see, the damage done on the way in and on the way out are the same, but antiprotons deliver twice the radiation to the target. Compared to protons, antiproton simulators also offer a more accurate measurement of tumor volumes by pinpointing the precise stopping point. Upon annihilation, they produce subatomic particles called pions, which are able to be detected external to the patient and imaged in 3 dimensions. It is speculated that the current methods of creating, capturing, and cooling antiprotons is no longer ideal. Future changes to these methods would result in larger production numbers of antiprotons that would be needed to fulfill the requirements for cancer therapy. There is no question that more research and resources are needed before antimatter use in radiation therapy can become feasible. More facilities need to focus on making antiprotons, and better methods need to be identified. The wave of the future is upon us, and antiprotons are the best particles for cancer therapy.